Hello everyone. Welcome to webinar number 7 in the Highway Safety Manual Training Series. This series is sponsored by the Florida Department of Transportation. The webinar series is offering training on AASHTO's Highway Safety Manual. This manual is also known by its acronym HSM. This particular webinar will present the material in HSM Chapter 18, which addresses freeway safety. I should note that Chapter 18 was not part of the HSM's 2010 release. Rather, Chapter 18 was published in 2014 as part of the 2014 supplement to the HSM. My name is Jim Bonison, and I welcome you to this webinar. I'm a senior principal at Kittleson & Associates, and my office is in College Station, Texas. If you have any questions after the webinar, please send me an email at the address shown here in the middle of the slide, and I'll get back to you as soon as I can. There are 2 learning objectives for this webinar. One is to inform you about the safety impacts of several freeway design elements and traffic control features. A second objective is to demonstrate the use of the HSM to compute the average crash frequency of a freeway segment. There are 3 main points that I want to make during this webinar. My goal is to make these points as we go through the presentation. First, predictive models provide a scientific basis for reliably estimating the average crash frequency of a freeway segment. Second, many freeway design elements and traffic control features can have an effect on safety. And third, any given design element or traffic control feature may affect the frequency of some crash types or severities more than it does others. So, for example, head-on crash frequency may be more greatly influenced by median width than by outside shoulder width. This webinar is the 7th of 9 webinars. The previously conducted webinars can be found on the Florida DOT's Office of Safety website. The next webinar will be conducted in the very near future. The content of today's webinar originates from Part C of the HSM. This part includes the safety prediction methods for various roadway facility types. Today's webinar is focused on Chapter 18, which contains the predictive method for freeways. This slide identifies several websites that provide useful information to support and guide HSM-related safety evaluations. Most notable is the first website listed, the Florida DOT HSM website. This website provides links to most of the other resources that I've listed here. The presentation today consists of 6 lessons. We'll take them in the order listed here. In the first lesson, we'll talk generally about using the HSM predictive method for freeway safety evaluation. Then, in the second and third lessons, we'll talk about the safety performance functions, or SPFs, and the crash modification factors, or CMFs, that make up the predictive method. In the fourth lesson, I'll show you how the method is used to evaluate a freeway segment. In Lesson 5, I will demonstrate the use of spreadsheet software to automate the freeway segment evaluation process. Finally, I'm going to wrap up the presentation and take some of your questions in Lesson 6. So let's get started. Lesson 1 has 3 topics of discussion. They are the predictive model, the predictive method, and the segmentation process. The predictive model includes 3 components. First, it includes a safety performance function. It includes multiple crash modification factors, and it includes a local calibration factor. These model components are multiplied together to estimate the predicted average crash frequency for any site of interest. The HSM tells us that a predictive method consists of two things. One is a set of predictive models, which we have just discussed, and the second is the guidance for using these models. This guidance consists of an 18-step process that is used to evaluate the safety of a site or a group of sites or an entire roadway facility. In the Freeways chapter, a site is considered to be a freeway segment or could be a speed change lane. In the interest of time today, we're only going to focus our discussion on freeway segments. The software that implements the method also follows the 18-step process. The first 6 steps consist of data assembly activities that are completed by the analyst. Step 7 then calls for initiating the calculations within the software. The software, of course, then automates these calculations and hence the remaining steps in the process. Today, we're going to focus our discussion on the first 6 steps because they can be the most challenging. The first step in the predictive method is to identify the project limits. In step 1, we define the limits of the freeway section of interest. These limits will depend on the purpose of the study. The study may address an entire project, or our study may just focus on a short length of roadway in one portion of the project. The project limits may include just one site, or they may include several sites. The location of each site is defined using a reference line. The analyst needs to establish this line early on in the process. In addition to location, this line is also used to determine the length of various roadway design features, such as curve length. The reference line is defined to coincide with the inside edge of traveled way for the roadbed that serves traffic moving in the increasing milepost direction. This line is shown in the figure at the bottom of the slide. The figure shows a plan view of a 4-lane freeway. Travel from left to right is shown to be in a direction of increasing milepost. So this is the travel direction that is used to define the reference line. In fact, the reference line is shown here in the slide by the arrow pointing to the inside edge of traveled way for the left to right travel direction. The second step of the predictive method is to define the study period. This period represents the consecutive years for which an estimate of the predicted average crash frequency is desired. The study period could represent 1 or more years in the future or 1 or more years in the past. Or in fact, it could represent both years in the future and years in the past. For example, the study period for a proposed project could be defined to start in 2016 and last 10 years. Thus, the study period would extend from 2016 to 2025. Step 3 requires us to acquire traffic data and crash data. The crash data are needed only if the empirical Bayes adjustment is applied. Sometimes we would call this the EB adjustment. In the interest of time, we will not be discussing the EB adjustment in this webinar. As far as traffic data goes, we need AADT volumes for at least 1 year in the study period. Volumes for missing years can be estimated according to a procedure that's described in step 3 of the HSM. To evaluate a freeway segment, AADT volumes must be provided for the segment itself and for the 4 nearest ramps. We're going to talk about how to identify the 4 nearest ramps in the next slide. Step 4 is to acquire geometric design data. These data include alignment variables like curve radius and curve length, and cross-section variables like lane width and shoulder width. Also needed is the distance to the 4 ramps nearest to the segment. Guidelines are provided in Chapter 18 for identifying these ramps. In general, they are the first exit ramps downstream of the segment in both travel directions, and the first entrance ramps upstream of the segment in each travel direction. If the distance to a ramp exceeds a half mile, then the ramp is considered to be too far from the segment to influence its safety. And in this case, the distance to the ramp is not needed. The volume of these nearby ramps is also needed. Again, this is an ADT volume. And we only need these volumes provided that the ramp is within the 1/2 mile of the segment. If it's further from that, then the safety doesn't influence that of the segment. This is a very brief overview of the input data. But be aware that section 18.4.2 of chapter 18 does provide a detailed description of all the required input data. During step 5 of the method, we divide the project into its component sites. These sites can be freeway segments or speed change lanes. The figure at the bottom of the slide shows a typical speed change lane. The area with gray shading represents the speed change lane site. The figure shows the site as including the ramp acceleration lane and the 3 adjacent through lanes. The median and the freeway lanes for the other travel direction are not shown in this figure because they are not part of the speed change lane site. The left and right boundaries of the speed change lane are defined by the gore point and the taper point. These 2 points are shown in the figure here at the bottom of the slide. Once the site boundaries are established, the data acquired in steps 3 and 4 are assigned to the appropriate sites, and that assignment completes step 5. The process of dividing the freeway into sites is called segmentation. The segmentation process will be discussed in a few minutes, but first I want to finish the discussion of steps 6 and 7. Next up is step 6. For this step, we assign reported crashes to the individual sites based on crash location. This step is applicable only if the EB adjustment is being applied on a site-by-site basis. Otherwise, we can skip this step. In step 7, we initiate the calculations of the predicted crash frequency for the sites that comprise the project. These calculations proceed on a site-by-site and year-by-year basis. When the calculations are finished, crash frequency estimates by severity level and crash type are available for each site. These estimates can be added together to describe the total crash frequency for the overall project. Okay, so let's talk about the segmentation process. It involves dividing a facility into sites. One type of site is described as a freeway segment, which is a short length of freeway that has a constant cross-section. A second type of site is a speed change lane. The illustration in the upper right corner of this slide shows a plan view of an interchange and a length of freeway. The freeway is shown to support travel in the left to right and right to left directions. There's one exit ramp and one entrance ramp for the right to left travel direction. The illustration in the bottom of the slide shows the freeway after it has been divided into sites. There are 3 freeway segments. They're labeled FR1, FR2, and FR3. There's also 2 speed change lane sites labeled SCEN and SCEX. I should point out that the freeway segments cannot, by definition, include speed change lanes. You can see that the first and last freeway segments, that is FR1 and FR3, have a piece missing from them that corresponds to the adjacent speed change lane. For each of these 2 freeway segments, we account for this missing piece of roadway by computing an effective segment length. The equation for computing this length is shown near the bottom of the slide, just above the long freeway segment. This equation is a bit small here in the slide, but it's also described in chapter 18. One key segmentation rule is that at gore points, one segment must end and a new one must begin. In other words, a new site always begins at a gore point. The gore point is defined as the point where the marked gore is 2 feet wide. This point is shown in the figure at the bottom of the slide. The figure shows a plan view of the outside freeway lane and a single lane exit ramp. A new freeway segment starts at the gore point that's shown in this graphic. This new segment is shown in the figure as a box that is outlined by a dashed line. Once the gore points have been identified and the corresponding segments located, the freeway section of interest is further evaluated for homogeneity or consistency in its basic characteristics. If there's any significant change in character, the freeway section is subdivided into segments. Criteria that define what constitute a significant change in character are provided in section 18.5 of chapter 18. The goal is to divide the road section into segments that are homogeneous in all characteristics that influence safety. Characteristics that are related to safety include those that are characterized as geometric variables and traffic volume variables. Key geometric variables include the number of lanes, lane width, shoulder width, median width, and clear zone width. A significant change in any one of these attributes constitutes the ending point of one segment and the start of a second segment. This slide shows a very simple example of the segmentation process using a section of urban freeway. The direction of increasing milepost is from left to right, so the beginning segment 1 is defined by the project limits on the left side of the slide. Now this section of freeway has weaving sections on both sides of the roadway and on both sides of the interchange. As a result, there's no speed change lanes for us to identify, which simplifies this example even a little more. Now, even though we have weaving sections, we do have gore points. And given this arrangement, segments 2 and segment 3 begin at the location of these gore points for the diamond ramps. Now, segment 4 begins at the location where the median width changes due to the convergence of the mainline road beds. Segment 4 ends at the project limit on the right side of the slide. Okay, so let's take a quick poll to see if everyone is connecting with some of the concepts that I've presented. Please indicate the one choice that correctly answers this question. Which of the following is a type of site that can be specifically evaluated using the HSM three-way method? A, signalized intersection. B, speed change lane. C, collector-distributor road. The correct answer is B, speed change lane. The collector-distributor road segment is evaluated using the method in Chapter 19 for ramps. Signalized intersections are evaluated using the methods in HSM Chapters 10, 11, or 12. We're now ready to start with Lesson 2. In this lesson, we will get acquainted with the various safety performance functions in the freeway method. A safety performance function is used to predict the average crash frequency for a site that has base conditions. In general, a site with base conditions has typical geometric dimensions. For freeways, the SPFs have many base conditions, such as 12-foot lanes and 10-foot outside shoulders. An example SPF is shown in the middle of this slide. It includes the variables A and B, which are regression coefficients that were obtained by fitting the SPF to crash data. The values for these coefficients are provided in the HSM. The SPF also includes a variable for the segments ADT and length. When this SPF is used for freeway segments, the length that's used is in fact the effective segment length. which excludes the length of any speed change lane that may be adjacent to the segment. The regression coefficients A and B can have different values depending on the crash type and severity being predicted. This table shows a sample of coefficient values for rural freeways with 4 lanes. Additional coefficients are available in Chapter 18 for other combinations of area type and number of lanes. The figure in this slide shows the relationship between AADT and the predicted average crash frequency for a freeway segment that is 1 mile in length. The x-axis shows the freeway AADT. The y-axis shows the predicted frequency of fatal and injury multiple vehicle crashes. The solid trend lines correspond to urban freeways, and the dashed lines correspond to rural freeways. The numbers near each trend line indicate the number of lanes on the freeway. The SPF for freeway segments predicts an increase in crash frequency as traffic volume increases. For a given volume, the model predicts fewer crashes when the area type is rural as compared to urban. The model also predicts fewer crashes when the number of lanes is increased. In other words, more lanes equal fewer crashes. This slide lists the base conditions associated with the freeway SPFs. For the SPFs that predict multiple vehicle crash frequency, the base conditions include no horizontal curvature, 12-foot lane width, 6-foot inside shoulder width, 60-foot median width, no median barrier, and no ramps within a half mile of the segment. These base conditions also apply to the SPFs that predict single vehicle crash frequency. However, the single vehicle SPFs also have some additional base conditions that apply. These conditions include 10-foot outside shoulder width, no rumble strips present, 30-foot clear zone width, and no barrier along the outside of the roadway. This is the first example application. It demonstrates the use of an SPF to compute the predicted crash frequency for a freeway segment. The scenario is a freeway segment on a rural 4-lane section of I-10 east of Tallahassee. And before we go to the next slide, I should note that this segment of freeway does not have any speed change lanes adjacent to it or within 1/2 mile of it. In this example, we're going to demonstrate the use of an SPF to estimate the predicted crash frequency. Specifically, we're going to use an SPF to estimate the predicted multiple vehicle fatal and injury crash frequency for the rural freeway segment. The data that we need are listed here on the left side of the slide. We have an AADT of 43,500 vehicles per day and a segment length of 0.75 miles. All geometric elements have a dimension that matches the base conditions, and the local calibration factor is 1.0. The predictive model form is repeated at the top of this slide. We saw it first back in slide number 9. For this example, all CMF values are equal to 1 because the corresponding geometric variables are at their base condition value. The calibration factor is also 1. So mathematically, the estimate from the predictive model is effectively equal to that from the SPF. The SPF coefficients A and B were shown previously in slide 24. For this example, the values we need are minus 5.975 and 1.492. After we insert these values in the SPF, the predicted value is computed as 0.531 multiple vehicle fatal or injury crashes per year. Okay, so let's continue the example by computing the frequency of the other 3 combinations of crash type and severity. Specifically, let's compute the predicted multiple vehicle PDO crash frequency, single vehicle fatal and injury crash frequency, and single vehicle PDO crash frequency. We can then add up these estimates to obtain an estimate of the predicted total crash frequency. So you may recall that we previously computed 0.531 multiple vehicle fatal or injury crashes per year. We're going to use the SPF again for each of the 3 crash type and severity categories that were identified in the question that we're now attempting to answer. As before, the SPF coefficients A and B are taken from the table in slide 24. For the multiple vehicle PDO crash frequency, we compute 1.146 crashes per year. This result is shown in the second box from the top of the slide. Continuing, we can compute 1.024 single vehicle fatal or injury crashes per year and 2.186 single vehicle PDO crashes per year. We can now add these 4 values together to obtain the predicted total crash frequency of 4.887 crashes per year. So let's take another poll to see if everyone is connecting with the concepts that I've presented thus far. Please indicate the one choice that correctly answers this question. Which of the following items are included as a variable in the freeway segment SPFs that are used in the HSM freeway method? Choices: A, median width; B, ramp AADT; C, segment length. The correct answer is C, segment length. Freeway AADT, the local calibration factor C, and calibration coefficients A and B are the other variables in the SPF. Okay, so we're now ready to start with lesson 3. In this lesson, we will get acquainted with the various crash modification factors in the freeway method. There are 11 CMFs available for freeway segments. Most of them are functions of geometric variables like lane width, shoulder width, or curve radius. They use the same base conditions as the SPFs. The CMFs can be used to adjust the estimate from the SPF to account for any non-base conditions that may exist on a segment of interest. The CMFs were calibrated to work in combination with each other such that they are unlikely to overestimate the safety influence of any specific geometric element. This slide lists the 11 CMFs that are available in the freeway method. For example, there is a horizontal curve CMF and a lane width CMF. In the next few slides, we will look closely at a few of these CMFs. However, we will not be able to look at all of them in the time that we have available to us today. This slide illustrates the lane width CMF. The equation for this CMF is shown at the top of the slide. It is used to compute the CMF for fatal and injury crashes. I should note that no CMF is provided for PDO crashes because the data examined by the researchers did not show a definitive trend between lane width and PDO crash frequency. The variable W subscript L represents the average lane width. The base condition lane width is 12 feet. The relationship between the CMF value and lane width is shown in the figure. The x-axis represents the lane width ranging from 10.5 to 14 feet. The y-axis represents the corresponding CMF value. The brown and red lines in the figure show how to determine the lane width CMF for 2 different widths. For the base condition width, which is 12 feet, you locate 12 on the x-axis, go up the vertical, brown vertical line to the CMF trend line, and then follow the horizontal line over to the y-axis where we find the CMF value of 1.0, as we expected for a base condition. Now consider a freeway segment that has 11 foot lengths. You locate 11 on the x-axis, go up the red vertical line to the CMF trend line, and then follow the red horizontal line over to the y-axis. There we find a CMF value of 1.04. The value of 1.04 tells us that since the segment's lane width is narrower than base conditions, the segment is expected to experience 4% more crashes than a segment with base conditions. This slide illustrates the inside shoulder width CMF. Two equations are shown at the top of the slide for computing the CMF value. The first equation is used to compute the CMF for fatal and injury crashes. The second equation is used to compute the CMF for PDO crashes. The variable W subscript IS is the paved inside shoulder width. The base condition inside shoulder width is 6 feet. The relationship between the CMF value and inside shoulder width is shown in the table near the middle of the slide. The values shown indicate that the CMF value increases as the shoulder width is reduced. This slide illustrates the outside shoulder width CMF. The two equations shown in the top half of the slide are used for computing the CMF value. The first equation is used to compute the CMF for fatal and injury crashes. The second equation is used to estimate the CMF for PDO crashes. The CMF value is different for curved roads than it is for tangent roads. The variable P subscript C is used to estimate the correct CMF value when a portion of the segment is curved. For example, if 1/2 of a segment is curved, then the P subscript C variable equals 0.5. The variable W subscript S represents the paved outside shoulder width. The base condition outside shoulder width is 10 feet. Now, I should note that this CMF is only applicable to the prediction of single vehicle crashes. The data that was examined by the researchers did not show an influence of outside shoulder width on multiple vehicle crash frequency. The relationship between CMF value and outside shoulder width is shown in the table. The values shown apply when there is no curvature. They indicate that the CMF value for fatal and injury crashes increases when the shoulder width is reduced. The CMF value for PDO crashes is unchanged. Okay, so this is the second example application. It demonstrates the calculation of CMF values using the equations that we've just discussed. The scenario is a freeway segment on a rural 4-lane section of I-10 just east of Tallahassee. In fact, it's the same segment that we used in the first example. In this example, we're going to demonstrate the calculation of several CMF values. Specifically, we're going to compute CMF values for the inside shoulder width and the outside shoulder width. The data that we need are listed on the left side of the slide. We have an inside shoulder width of 4 feet and an outside shoulder width of 11 feet. Now, we should also note that there are no horizontal curves on this segment. Okay, so let's first compute the inside shoulder width CMFs. We saw the two equations for this CMF back on slide 37. They're repeated in the top half of this slide. We substitute the inside shoulder width of 4 feet into each equation and compute a value of 1.035 for the CMF applicable to multiple vehicle fatal and injury crashes. We can also compute a value of 1.031 for the multiple vehicle PDO crashes. You may recall from slide 37 that the CMF equation for fatal and injury crashes is equally applicable to both multiple vehicle and single vehicle crashes. Now, this relationship is shown in the third box from the top of the slide, where the CMF value for the single vehicle fatal and injury crashes is shown to equal the 1.035 that we already computed. Now, for similar reasons, the CMF value for single vehicle PDO crashes is equal to 1.031, which is shown in the box at the bottom of the slide. Okay, now let's compute the outside shoulder width CMFs. We saw the two equations for this CMF back on slide 38. The CMF equations are repeated in the top half of this slide. Since there are no curves on the segment of interest, the variable P subscript C has a value of 0, which really simplifies the equations by eliminating one term. We substitute the outside shoulder width of 11 feet in each equation and compute a value of 0.937 for the CMF applicable to single vehicle fatal and injury crashes. And we also compute a value of 1.0 for single vehicle PDO crashes. And you may also recall that from slide 38, that is, that the CMF does not apply to multiple vehicle crashes. So let's take another poll to see if everyone is connecting with some of these concepts. Please indicate whether the following statement is true or false. Based on the HSM Freeway method, the predicted crash frequency will increase if the average lane width for a freeway segment is reduced and there are no other changes. Now, by no other changes, I mean all other dimensions stay the same. The correct answer is true. The predicted crash frequency will increase if the average lane width is reduced and there are no other changes. Okay, we're now ready to start with lesson 4. In past lessons, we learned about SPFs and about CMFs. In this lesson, we're going to put everything together. Specifically, we're going to use the SPFs and CMFs in a set of predictive models. And we're going to use these models to evaluate one specific site. And I've prepared an example application to help us do this. This is the third example application. It demonstrates the use of a set of predictive models to compute the predicted crash frequency for a freeway segment. The scenario is a freeway segment on a rural 4-lane section of I-10 east of Tallahassee. It's in fact the same segment that we used in the first two examples. The question we will address first is, what is the multiple vehicle fatal and injury predicted crash frequency for the rural 4-lane segment? The data that we need are listed on the left side of the slide. We have an inside shoulder width of 4 feet and an outside shoulder width of 11 feet. We should also recall that there are no horizontal curves in this segment, and the local calibration factor is 1. All right, to answer the question at hand, we need to apply a predictive model. The model is shown in the box in the middle of this slide. In example 7a, we computed the value of the SPF for multiple vehicle fatal and injury crashes. It was 0.531 multiple vehicle fatal and injury crashes per year. In example 7b, we computed the value of the CMF for a 4-foot inside shoulder width. For multiple vehicle fatal and injury crash frequency, this CMF was determined to have a value of 1.035. Also in example 7b, we noted that the CMF for outside shoulder width for multiple vehicle fatal injury crash frequency was not applicable, so we do not include this CMF in the calculation. So now we have all of the necessary values. We can plug them into the equation and compute the predicted crash frequency as 0.549 multiple vehicle fatal and injury crashes per year. Using the same approach as we did in the previous slide, we can now compute the answers to the two questions posed in this slide. The first question is, what is the predicted multiple vehicle PVO crash frequency, single vehicle fatal and injury crash frequency, and single vehicle PVO crash frequency? The second question is, what is the predicted total crash frequency for the segment? The answer to the first question is obtained by the application of the predictive model for each combination of crash type and severity. The calculation mechanics are the same as we used when we computed the multi-vehicle fatal and injury crash calculation. So in the interest of time, I'm not going to show the equations here. And you should recall that the SPF values we need were computed in example 7a. These values are listed in column 3 of the table shown in this slide. Similarly, the CMF values we need for inside shoulder width and outside shoulder width were computed for example 7b, and these values are listed in columns 4 and 5 of the table. So the answers to the first question can be computed, and they are in fact shown in the last column in rows 2, 3, and 4. They are outlined by the box with a thin red line. We computed 1.182 multi-vehicle PVO crashes per year, 0.993 single vehicle fatal and injury crashes per year, and 2.254 single vehicle PVO crashes per year. To answer the second question, that is, what is the total predicted crash frequency, we just add up these four values and compute a value of 4.978 crashes per year. Of course, we could round that to a nice round number of 5.0 crashes per year. Okay, so we're now ready to start with lesson 5. In this lesson, we will get acquainted with the Enhanced Interchange Safety Evaluation Tool. Its acronym is spelled ISATE, and it's often pronounced as ISATE. It's a software tool that automates the Freeway Predictive Method. Now, ISATE is an Excel spreadsheet. It uses macro code for most of its calculations. It can be used to evaluate an individual site or an entire freeway facility. The sites can consist of any combination of freeway segments, speed change lanes, ramp segments, and crossroad ramp terminals. ISATE can also be used to evaluate a freeway facility that's comprised of several sites that form a section of freeway or even an interchange. ISATE is comprised of 11 worksheets. These worksheets are listed here, and the use of them will be discussed in the next few slides. If you have a copy of ISATE software and your computer is in front of you, now is a good time to open your copy and follow along with me. One of the 11 worksheets is the Welcome worksheet. It's the first worksheet that you see when you open ISATE. You can see that the top portion of this, in fact, you can see in this slide the top portion of the Welcome worksheet. The color-coded tabs on the bottom of the spreadsheet are used to access the other worksheets. These tabs are highlighted using a red rectangle at the bottom of the slide. In the interest of time, we're going to focus our discussion today on just 3 of the 11 worksheets. These are the most commonly used worksheets when evaluating a freeway section. The 3 worksheets that we need are the main worksheet, the Input Freeway Segments worksheet, and the Output Summary worksheet. Their use consists of the 4 steps that are listed at the bottom of the slide. The first step consists of inputting basic data in the main worksheet. The second step consists of entering site data in the Input Freeway Segments worksheet. The third step consists of returning back to the main worksheet and starting the calculations. And the fourth step consists of reviewing the results in the Output Summary worksheet. This slide shows a portion of the main worksheet. The cells in this sheet, and in fact all other sheets, are color-coded. Many of the cells in the worksheet are white or gray. These cells contain descriptions, labels, or heading information. Some of the cells are blue. These cells are used to input the data that describe the site or sites being analyzed. Many of the white or gray cells have a red rectangle in their upper right-hand corner. When the mouse cursor is placed over a red triangle, a message box appears. The message contains information that will clarify the requirements for measuring or entering input data. One of these message boxes is in fact shown here in the middle of the slide. This slide shows a portion of the Input Freeway Segments worksheet. Each segment is allocated 2 columns if the EV adjustment is used, and that's the case as shown in this slide. However, each segment is allocated only 1 column when the EV adjustment is not used. Several functions are provided in this sheet to manage the data that are entered. These functions are activated by clicking one of 2 buttons in the upper left portion of the worksheet. These buttons are highlighted in the slide using a blue oval. One button is used to clear input data from the worksheet. This action is performed by clicking the Clear button. The second button is used to check input values. This action is performed by clicking the Check Input Values button. Advisory messages will appear after this button is clicked if there are any issues with the input data. Advisory messages are updated every time the Check Input Values button is clicked. This button should be used every time data are entered, and it should be reused until all issues are addressed and no advisory messages appear. The rows in the input data worksheet are arranged in logical groups to facilitate data entry. There are 7 groups in this worksheet. Within each group, there's a heading, and it's shown in a row with a gray background. Each group corresponds to one of the data entry sections listed on the left side of this slide. Collectively, these groups describe the geometry, the traffic volume, and crash history for each segment. This slide shows a portion of the Output Summary worksheet. This worksheet provides aggregated results for an entire facility. It also aggregates the results by facility component, by year, by crash type, and by crash severity. So let's take a closer look at this output data. The box at the top of this slide shows a portion of the graphic that we saw in the previous slide. Specifically, it shows the crashes for the entire facility. This particular table summarizes the estimated number of crashes during the study period. It also summarizes the estimated crash frequency for the entire facility. It provides these measures for total crashes and for each severity level, K, A, B, C, and PDO. The box in the middle of this slide shows the crashes by facility component. This table summarizes the estimated number of crashes for each of the facility components, which include freeway segment, ramp segment, and crossroad ramp terminals. It provides these measures for total crashes and for each severity level. The total present value of the crashes is shown in the box at the bottom of the slide. This value represents the sum of the crash costs at all sites for all years in the study period. All right, let's take another poll to see if everyone is connecting with the concepts presented. Please indicate the one choice that correctly completes the following statement. The ISATe software can be used to evaluate the following. A, freeway segment. B, freeway speed change lane. C, ramp segment. D, crossroad ramp terminal. And E, all of the above. The correct answer is E, all of the above. ISATe can be used to evaluate any of the site types that are listed on this slide. We're now ready to start the last lesson. I plan to cover the limitations of the HSM Freeway method and to make a few closing comments. The Freeway methodology in Chapter 18 addresses many things, but there are a few that it does not address. It does not address some design conditions that are listed here on the slide. Specifically, the method does not address freeways with 11 or more lanes in urban areas, or those freeways with 9 or more lanes in rural areas. It does not address freeways with continuous access HOV lanes, or those with buffer-separated HOV lanes. In contrast, the method can address the general purpose lanes of a freeway that has a barrier-separated HOV lane. In this case, the separating barrier must be either guardrail or a concrete safety shade. Now, to continue, the method does not address freeways with ramp meters, safety shoulders used as travel lanes, doesn't address toll plazas, and it doesn't address reversible lanes. As I noted back in one of the first few slides, there are 3 main points that I wanted to make during this webinar. The first was that the predictive models provide a scientific basis for reliably estimating the average crash frequency of a freeway. Second, many freeway design elements and traffic control features can have an effect on safety. And third, any given design element or traffic control feature may affect the frequency of some crash types or severities more than it does other types or categories. I hope you can see the justification for these points based on what we've discussed today. Well, thanks for attending this webinar. We certainly appreciate your taking the time to be with us today, and we're now going to go live to answer some of your questions in the time remaining.